Record. Okay, so what I want to do today is really work on carbohydrates. We didn't do oligosaccharides or polysaccharides, which I'm going to cover today. But I want to review some of the details on carbs. It's a real involved chapter, and it deserves quite a bit of time. Are there any questions before we go on? We're having our alcohol phenol lab today and Wednesday. Okay, so let's jump over here. Okay, so I want to review, before we get into oligosaccharides, I want to review disaccharides and some of their subtleties. Remember, a disaccharide is made up of two monosaccharides, and there is a linkage between them. So all saccharides that are above a mono have linkages. And those linkages are how the anomeric carbons hydroxyl group, which is right here, how those are when it hooks up. Is it in the alpha position downward or the beta position upward? So let's get some room here. Now, one of the disaccharides that I want you to know is maltose. Let's do this. Okay, so let's just a common question I would ask on a test. I would show you maltose. So actually, I wouldn't say it was alpha. I would say, in fact, I wouldn't. I would just say, here's a disaccharide. Name it. Include alpha and beta. For two, is it a reducing sugar? Now, remember, reducing sugar, you look for the hemiacetal. What is the linkage? Those are three questions I would ask you on a lot of these mono-di oligosaccharides. Okay, so first of all, naming it, okay, we have glucose, and this happens to be an alpha glucose tied together, okay? And if it's tied together in this linkage here only, because there are other linkages, but only this one categorizes it as maltose. So This anomeric carbon before linkage is in the alpha position. And that's carbon number one.
And I tried to get my mom to fix it, but she could.
I didn't understand you. You were very muffled. Say again. Okay. And it's hooking up, but this is carbon number four. Now remember the numbering on these goes 1, 2, 3, 4, 1, 2, 3, 4. And then 5, 6. Carbon number one with 6 membered rings is always carbon number one. Okay, so this is carbon number four. It's hooking up to. So that's the linkage. It has to be an alpha 1,4 linkage. 2 glucoses together. If that's true, it's maltose. And because this goes down, it's alpha maltose. Okay, question number 2. Is it a reducing sugar? Look for the hemiacetal. That's right over here. This is not a hemiacetal. This is a full-blown acetal because there's no OH there. So that would be yes. And why? We would point to the hemiacetal. And then the linkage is going to be alpha 1, 4. That is a typical question on the next test. Okay. Now we could ask the same question if we had a monosaccharide. For example, let's see, let's do the same question. Come on now, cooperate. Okay, so let's look at a monosaccharide. Okay, name it. All right, this is galactose. Notice that carbon number 4 here goes up rather than down, where glucose it goes down. And this goes down, so this is alpha galactose. Is it a reducing sugar? Look for the hemiacetal. It should be right here. So that would be yes. What's the linkage? Okay, does a linkage exist with a monosaccharide? Well, what's the definition of a linkage? You guys. Excuse me. All right. Okay, linkage connects monosaccharides together. Alpha, beta, depending on the anomeric carbon. Here's the anomeric carbon here. Okay, so is there a linkage with a monosaccharide?
No.
No, because a linkage, you're connecting up two monosaccharides. So if you just have a monosaccharide, it's not connecting to anything. So there is no linkage with monosaccharides, only with di, oligo, and polysaccharides we have linkages. Okay, so this kind of analysis, naming it, is it reducing sugar? What's the hemiacetal? What's the linkage? Okay, so I'm going to do one more disaccharide. And that is this guy here. Now, if you look this up online, sometimes a structure doesn't look like this. It's more of a horizontal version of this. And they've taken in my class, we're always going to draw the anomeric carbon to the right. In various textbooks, sometimes they draw the anomeric carbon on the left side just for printing purposes. So it's simpler for them to print it, but it's not consistent with the literature. Literature, if you look up a peer-reviewed article and they mention fructose, frequently they'll put it this way, vertically, where the anomeric carbon is on the right. Okay, so let's look at this guy. Okay, we start with glucose on the top. And in an alpha position, the OH is going down. Okay, so same set of questions here. Okay, so name it. Okay, I'm going to name this fructose. Now, fructose is not an alpha or beta because there's no hemiacetal present. If there's no hemiacetal present that goes up or down, it's neither alpha or beta. Okay, so all the anomeric carbons are connected, as opposed to up here, where we have an anomeric carbon that's not connected to anything. So then it's going to be an alpha or beta. So since fructose does not have the hemiacetal present, it's neither alpha or beta. Okay, so the alpha beta naming only applies if there is a hemiacetal present. Now, fructose by itself has a hemiketal, which can be alpha or beta. Glucose by itself can either be alpha or beta because it's got a hemiacetal present. Fructose, now let's just analyze this fructose here. Okay, we have, let's make this big. Okay, so we have two OCOs here. All disaccharides have two OCOs. Okay, so here's the first one. Let's do the top one first. So we have OCO. Let's do the 3 steps. So that's a yes. Is there an OH present? No. And is there an H present? Yes. And there's an H right here. Okay, so because there's no OH there, that means that is an acetal. Let's do the analysis down here. Okay, we have O, C, O, so that's a yes. Number 2, is there a hydroxyl present? No. And do we have an H present right here? No. So I mean that is a ketal. So remember the 1, 2, 3. It's 1, C, OCO present. OH present. H present. Okay, so we have an acetal and a ketal. We do not have an hemiacetal. So is this a reducing sugar?
No.
That's correct. It's not a reducing sugar because there's no hemiacetal present. Why? No hemiacetal. Okay, what's the linkage? Let's look at the linkage now. Remember, the linkage always has 2 parts. So we're starting with the anomeric, anomeric carbon up front, or on top, I mean. So that's going to be the OH, when it started, is in the alpha position, and it's anomeric carbon number 1. So the linkage is going to be starting with alpha 1. Down here, because the OH is going up, it's going to be a beta. And it's on carbon number 2, because this is carbon 1, carbon 2. So on 5-membered monosaccharides, the anomeric carbon is in carbon number 2, not 1. So the linkage is going to be alpha 1, beta 2. Alpha 1 because anomeric carbon number 1 and it's going down in the alpha position. Beta 2, anomeric carbon number 2, and the OH was going up when it started. That's what makes fructose. It's got to be alpha 1, beta 2. And it's not a reducing sugar. There's no hemiacetal present. Okay, so are there any questions about the analysis you go through? Okay, a good practice would be to go through what we've gone through so far. We talked about the 3 monosaccharides you need to know: glucose, galactose, fructose. Answer these 3 questions. The 3 disaccharides: maltose, lactose, sucrose. Look at the 3 questions as well. Okay. All right, are there any questions about this so far? And this is going to just take lots of practice, just over and over and over again. Okay, because we're going to jump into illegal saccharides now. The first one I want to talk about is raffinose. It's the simplest one. It's got 3 monosaccharides. Okay, and what is this guy down here? What disaccharide is that? It's sucrose. That's right. We just talked about right there, sucrose. Okay, and it has galactose tied in at carbon number 6 off the glucose. Let's look at its linkage. All right, so this is the anomeric carbon on that galactose. This carbon number 6 here on the glucose, carbon number 6 is free swinging. It's neither up, down, it's just free to rotate. It's a single bond here. It's free to rotate. So what it does, it swings around so that it's in the most stable configuration, keeping the oxygens as far away as possible so they don't repel each other as much. Okay, so we're not going to say this is alpha beta on the carbon number 6. Because this is galactose with the hemiacetal, we have that OH coming down that can be either alpha or beta. In this case, it's going to be alpha. So it's an alpha 1, 6. Glycosidic linkage. And then because this is sucrose, this is going to be the alpha 1 beta 2 we talked about a few minutes ago. All right. Now, this is a major carbohydrate in human breast milk. This says it's not a reducing sugar. Why?
No hemiacetal group.
Exactly. No hemiacetals. So it's not a reducing sugar. Hence, it cannot be oxidized. It's a prebiotic for infants. Prebiotic means it's food for bacteria that lives in your gut. Probiotics is a name that's associated with the bacteria in your gut. Also referred to as the microbiome. So the infant does not ingest the raffinose. It does not go through carbohydrate metabolism. What it does, it passes on through to the baby's gut where the bacteria feed on it. So it's very important to include this in all formula for infants if they're not breastfeeding. Cheap formula doesn't have it in it. Okay, so that's the first major illegal saccharide. The second one is we're just going to add another galactose on, then it's called stachanose. Okay, and stachanose is just another alpha 1,6 galactose stacked on to the top galactose here in the same linkage, an alpha 1,6 linkage stacked on top of the sucrose. So that's raffinose up here. If you know sucrose, it's pretty easy to tack on a galactose. If you know raffinose, it's easier just to tack on a galactose in the same position. What's interesting about saccharose is the major cause of flatulence whenever you eat certain foods like beans. It's a very good prebiotic. If you've ever heard of Beano, which reduces flatulence when eating beans, it basically converts this to, it takes off that, and leaves that. So it converts it to 2 galactose and 1 sucrose. Also, and this is, I get varying opinions on this. To soak your beans or not to soak your beans. A lot of people don't go through the trouble of soaking their dry beans. If you just eat canned beans, it's different. You're cooking with dry beans, though. Over the years, I've read more articles saying that if you soak your beans overnight and you toss the rinse water, the water the beans are soaking in, you will remove stachyos, or at least a major part of it, thus reducing the potential for flatulence. I've also read other articles, it doesn't make any difference. So I don't know. I like soaking them because they cook quicker, and in my opinion, they're more tender. But you got to have, 8 hours to soak them also. Okay, so that is one class of oligosaccharides. Is we have this string of 6-membered monosaccharides with sucrose. The other ones is we're stacking fructoses with glucose. Frequently, you'll see inulin, and inulin is used frequently for padding on capsules. They'll add this in just to kind of fill the capsule up. So it's considered an inactive ingredient. It's not a reducing sugar. There are no hemiacetals by themselves, so it's not a reducing sugar. And basically, we've got some number of fructoses stacked on top of the N-fructose. Now, some of you might say, well, what about this guy down here? Does that count as a hemiacetal? Well, let's do the test. Is there an OCO? Well, let's look at this now. We have an O there, a C there, a C there, and an O. So this is OCCO. Everyone see that? We go O, C, C, O. So this is neither an acetal or a ketal or a hemi, whatever, because it fails step number 1. So that's a no. And then we get to stop right there. So that doesn't qualify for a hemi anything. Oops. Okay, so that's one of the reasons this is not a reducing sugar. So there's no hemiacetal present. Now, as far as how many fructoses we have, if it's immune, it's greater than 11. 11 or greater. Now, let's analyze the linkages here. Okay, so we start with glucose up here. We start with glucose, and the original anomeric OH is going down. So we're starting with alpha glucose. Here we have fructose and carbon number 6. And that is free swinging. So so the first linkage is alpha 1,6. Down here is we have, this is carbon number 2. Notice the OH is going up here. That's in a beta position. Let's see. And these fructoses, both of them are in a beta position. This one here, you might say, is going down. That's alpha. But see, it's not an anomeric carbon. Alpha beta only counts for the anomeric carbon. So anomeric carbons in 6-membered rings, carbon number 1. 5-membered rings, it's carbon number 2. So this linkage is going to be beta 2, beta 2. This one would be alpha 1. Okay. And when we get to the carbohydrate lab, this is kind of the stuff you're going to be doing. You're going to be working with Benedict solution, barreling solution. There's a variety of tests. All of them are looking at the oxidation potential of the carbohydrate. In other words, is there a hemiacetal exposed to be oxidized by an oxidizing agent? In case of Benedict's solution, we have the copper +2 being oxidized to copper +1, and the format it ends up in is Cu2O. Same with this. And because sucrose has no hemiacetals, it can't be oxidized. So the oxidizing agent remains the same. So this is a standard diagnostic test for the whether the sugar is a reducing sugar or not. Okay, you need to know these 3 disaccharides. You need to know their linkages, what the sugars are that make them up. Not so much the source. Maltose was originally found in beer. That's hence the name maltose. Lactose is found in mammalian milk, frequently dairy. And then sucrose can be found in both cane and beet sugar. Not honey. Honey is an invert sugar. That means the fructose and glucose are separate. Okay. The three monosaccharides you need to know are these three here. Sounds like someone's at the door. Okay. Now, let's go on to the last major unit. Let me shut the door. Okay, polysaccharides. They're just really long saccharides. It can be thousands of units long. The main ones are starch, amylpectin, glycogen, cellulose. Those are the four. They're used a lot in cooking. They're used a lot in prebiotics. They're used a lot as intermediate compounds when, for example, when you're making fructose syrup, start with some kind of starch, usually cornstarch. And most of them are made of glucose units. And they have a particular linkage, the alpha 1,4 linkage. Okay, so this is called starch. Okay, all of them they're all glucose. And secondly, they all have alpha 1,4 linkages. That's alpha 1,4 linkages. Amylpectin has the same thing as starch, an alpha 1,4 linkage, but they also have a branch up on carbon number 6. And that is going to be an alpha 1,6 branch. And again, these are all alpha 1,4s. Excuse me. So starch and amylpectin are very similar. Lots and lots and lots of glucoses with alpha 1,4 glycosidic linkages, plus the branching, the alpha 1,6 branching. A common test for starch or amylpectin is to add iodine, I2, and that ends up forming a very dark spot. It's almost black. I think they describe it as a dark indigo. And it says starch iodine or amylpectin iodine complex. Glycogen is a close relative of amylpectin has more branching, and usually that's the animal starch. Glycogen is a place where our bodies can store energy, and we can store up glucose, and it's stored in both liver and muscles. The more you work out, the more you build up glycogen, and it's the more you work out exercising a specific muscle, That's where the glycogen is stored, in that location. So it's more readily available when that muscle needs it. So if you're doing arm curls where you're using your biceps a lot, and the glycogen over time is going to build up in those biceps. So when your biceps need energy, that's where it's nice and close. It doesn't have to come from the liver into the blood, chip to the biceps where it's needed. Instead, it's local. And the other major class of polysaccharides, instead of alpha 1,4, we're having beta 1,4, glycosidic linkages. And that's considered fiber. So that's what the cellulose structure looks like, and no branching. Oh, there aren't any more slides. All right, so that concludes our carb unit. So, let's talk about structures now. I want you to know. So those would be the monosaccharides. Okay, so these are flashcards, city. And then let's see here. Okay, assuming I spelled everything right. Okay, so I'm going to put this on Canvas.
I had a quick question.
Yeah.
So for the structures, I know how you said we'll have to name them and their linkages and stuff like that. Would we also have to know how to draw out every single one of those structures?
Yeah.
Okay, thank you.
That's why I'm saying flashcard city. And you know, once you know glucose, glucose is is so ubiquitous. I mean, it's just all over the place. That helps a lot. Then you just need to know how they're connected up. And galactose and fructose, um, not so much fructose. There's an illegal, I don't know if you remember the fructosides, the other illegal saccharide class. Uh, that's a minor class. So I'm not requiring you to know the structure of those. Other classes I have, and I don't know, I just decided that it's important to know about them, but not how to draw them. These are really important. You'll see these a lot. Okay. And did I spell stachyos? I don't think I spelled stachyos right. Okay. Okay. So let's practice some more here. Oh, I haven't included any of those. Let me zoom over here. Okay, so let's look at some past tests. Okay, so let's just go through this. Some of this is going to be a review on the aldehyde ketone, but okay, so let's not worry about naming these things. So we get into the more complex. All right, so beta galactose. Okay, galactose, 6-membered sugar. It's in the beta configuration. So that means beta is going to go up. So that would be beta galactose. That's the anomeric carbon. It's a reducing sugar because we have OCO and it's hemiacetal. So it's a reducing sugar. Fructose. Now, is there an alpha fructose? And alpha beta designation requires a hemiacetal. So remember with fructose, it can exist as a hemiketal, but fructose is one of those exceptions. So in our class, because it forms, let me draw it first here. Okay, so with just fructose by itself, I'm not sucrose, but just fructose by itself, it can be alpha beta, but it's not going to form a hemiacetal. It's going to form a hemiketal. So let's do the 1, 2, 3. Okay, so we have O, C, O, so that's a yes. Is there a hydroxyl present? Yes. Is there a hydrogen there? No. So that means it is,
Professor,
yeah.
I don't think it's showing your screen. Like the drawing or something.
You can't see this?
No.
Yeah, you're only showing Canvas right now.
Okay, let me try it again. Can you see it now?
Yeah, I could see it.
Okay. Sorry about, I don't know why it didn't show up. I was in a shared mode. Huh. Okay, I'll tell you what then, why don't we just start over? Thanks for letting me know. So let me ramble on and no one's going, what the heck is he talking about? Okay. Galactose. Okay, and it's in the beta form. Means the OH goes up. Okay, and then we have the anomeric carbon, carbon number 1. Okay, alpha fructose. Fructose is a little tricky because it's not, because one, it's a furanose, 5-membered ring, and secondly, it's still got 6 carbons. And it's alpha, so that means the OH on the anomeric carbon number 2 is going to be going down. So remember it, alpha or beta has to have a hemiacetal. Now, in some books, they don't distinguish between a ketal and an acetal. And the reason for that is there's a lot of exceptions to the rule of requiring a hemi or a hemiacetal, because a hemiketal can transform into a hemiacetal. It's a 2-step process. It's not that hard to do, but our class requires a hemiacetal to be a reducing sugar. So this is in terms of reducing sugar. Now, this is so let's analyze this now. We have OCO. So that's a yes. Do we have an OH present? Yes, off that anomeric carbon. Do we have a hydrogen present? No. So that makes that a hemiketal. So as far as our class is concerned, this is not a reducing sugar. And in some circles, they'll say, well, because of the exceptions, it turns into, and it just need to know reducing sugars. Hemiacetal present, yes or no, just making it simple here, okay? So hemiketals, we're going to say not a reducing sugar in here. And if you get in talking to someone else in another class, they may say, oh, well, it does blah, 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 blah. Don't worry about that. Just for our class, not a reducing sugar. Okay? Okay. All right, so I give you, this happens to be maltose. And because this hemiacetal is going down, it's alpha maltose. It'd be alpha maltose. Is it reducing sugar? Yes. Because there's a hemiacetal, which is going to be here. And okay, test you would use, you could use Benedict's. Okay, the glycosylic linkage here is going to be an alpha 1, 4. What is meant by the term reducing sugar? Opens up to an aldehyde via a hemiacetal. Which can be oxidized. What disaccharide has an alpha 1 beta 2 glycosidic linkage? That would be sucrose. So glucose goes in the top. Fructose goes on the bottom. So is it reducing sugar? No, because no hemiacetal present. So this linkage here is going to be an alpha 1 beta 2. Okay, so this is carbon number 2. This is carbon number 1, both anomeric. This linkage here is going to be beta because we're going up. And connecting with an alpha up here. Okay. Okay, so let's look at the structure. You've never seen it before. And I now printed, when my students received this test, the blue was not in blue, it was in dark gray because it's a black and white printer. So you have to identify that sugar. Okay. And what sugar is that? That is called glucose. Judging by the directions of the OH groups, OH goes down, up, down. And then in this case, we're going to have a beta acetal. So we go, so we have OCO, we have no OH, and we have an H. So that is an acetal. Is it a reducing sugar? No. No hemiacetal. And we circle it, it would be right here. What's the difference between cellulose and starch? Linkage. Alpha 1, 4 versus beta 1, 4. This would be starch. This would be cellulose. Okay, show the reaction of Benedict solution test with beta glucose. Okay, so we start with beta glucose. So that is beta glucose. And what happens with, because that's a hemiacetal, it can open up. To an aldehyde. And we put in copper +2 in an alkaline environment. Okay, the copper 2 is going to go to copper 1. That's the reduction. And then the aldehyde is going to the acid version. So this would be the acid salt. And this would be blue. And this is going to be kind of a I don't know, which would be the cuprous oxide. So that would be the reaction that we'd be looking for. Yeah, basically our next test is going to be on aldehydes and ketones in terms of acetals and ketals. Carbs, acids, esters, and lipids. So we haven't talked at all about acids yet, other than this reaction here. So acids can react with alcohols to form esters, and that's the basis of lipids. Okay, are there any questions about this reaction? Okay, and that was the test. And there's this aldehyde ketone stuff here as well. And I would probably, instead of asking the simpler aldehyde ketones, I would probably be asking things like that are in the worksheets I gave you on forming simple acetals. For example, drugs over here. So how would you make this? So this is a Ketal, how would you make it? Or another question would be, well, how would you make it? All right, let's look into that. Okay, so you've got a backbone. And because it's a ketal, you're going to start with a ketone with that same backbone. And we have 1, 2, 3, 4. Okay, and then a ketal has aldehyde, it's alcohol added. That's a 2-carbon alcohol. Let's see, let me give myself more room here. So we're going to add first ethanol, 2-carbon alcohol. That'll give us an intermediate product of now let's continue the backbone. So we have the backbone there. And then we have the alcohol here. Now we're going to add another alcohol. So this would be the ketone to start with. This is the hemi-ketal plus alcohol. Gives us the full-blown ketal. So that would be what I was looking for if I asked you how to make this. And then variations upon that. You start with a ketone and you add alcohol, what do you get? If you start with a ketal, another question would be the breakdown products. If we start with what would that break down to? Well, okay, so first of all, this is a OCO, so it's a hemi ketal. Hemi ketals break down to their original ketone. Here's the alcohol that was added, 2-carbon alcohol. So it's going to break down to the 2-carbon alcohol. So those are the two types of questions I'd ask. Is how to make a ketal or hemi-ketal, and then what are the breakdown products? Those are two you're going to see in that test. And then a bunch of carb questions. Now, this would be a good hour-and-a-half test, but we have lipids and acids. So have the number of carb questions in half. You're going to have all of them. You have about half of those. But these are the type of questions that I would be asking. Okay. And I may have a couple of take-home problems, maybe involving the testing, like the Benedict solution or some of the other carb test reactions. Yeah, I usually don't do that, but this is quite a bit of material. So, all right. Any questions about this guy?
Are you going to post this on Canvas as well in the files?
Say again.
Are you going to post the answer sheets to all of the practice exams for these chapters on Canvas as well?
I could.
That would be really helpful, like last time.
Okay, I think. Let me check one thing here. Trying to see if there's any here with answers or key. You can see I have a lot of old tests. I'll post a couple, 3 tests, and then I'll have an answer key.
Thank you.
And I can't see it. Trying to see if any of these have answers already. Oh, it looks like I have a few already. Won't take me long to do the keys though. Okay, anyway, yeah, I'll do that. Okay, that concludes our carb and aldehyde ketone subunit. Our next unit is going to be, and I'm going to lightly introduce that today. It's going to be on carboxylic acids. Okay, like acetals and ketals, we took an aldehyde or ketone and then added an alcohol to it. Well, if you take an acid and add an alcohol to it, you form something called an ester. So, frequently, you'll rarely in an organic class see that. You'll either see this or this. And or that. Carboxylic acids have been around a long time, mainly in the form of the biochemical side in terms of fatty acid. Now, these are some of the smaller carboxylic acids, depending on the length of the chain. Now, this is an interesting acid here. It's called butanoic acid or butyric acid. It is what makes cow patties smell. It is what makes cream smell and what makes butter smell when it gets old. And it's a 4-carbon acid. acids are really common in a biochemical world. The main important thing to remember about acids biochemical acids are very weak acids. They're not strong, except for one exception. That's hydrochloric acid in your stomach. Other than that, the acids are all very, very weak, very weak. And there's two kind of areas we're going to be talking about quite a bit in this unit or subunit. That's super long acids, organic acids. Those are called fatty acids. And they have a big long tail that's non-polar. Then they have a very, very, very polar head on them. So we have a hydrophilic and a hydrophobic part. And it depends on how long the tail is that'll get its characteristics as being non-polar or polar. Remember with alcohols, we had C7 alcohols tended to be non-polar. Alcohols, carbons 1 through 6 tended to be polar. It's going to be a similar concept with acids. We'll see some graphs in a little while here, where the length of the chain on the other end of the acid group will make it either polar or non-polar. Okay, so naming an acid. That's the functional group. That will always be carbon number 1. And then we're going to name it like we've been naming all along. 4 carbons, buta, and it's an oic acid. So butanoic acid, branching on carbon number 3, so 3-bromo-butanoic acid. And we write it in our class like this. You'll see it both with a dash for the branching and then also no dash. I like to separate them out so it's real obvious. This is a branch, backbone, functional group. Now, as far as aromatic acids go, we have aromatic acids based upon benzene with a COOH on it, or in line form. So this would be like this. So we have benzoic acid. And then we have 3,4-dimethyl benzoic acid. Okay, so here we're getting into this idea of low molecular weight carboxylic acids being very polar. Now, interestingly, carboxylic acids can form something called a dimer. And that is where they get a mutual bonding between the acidic groups. Very strong hydrogen bonding. Higher than alcohols. So similar molecular weights. We start with the alkane being the lowest. The acids now tip the alcohols by quite a bit. Well, here's our graph that we've been following along. So we have alkenes down here, aldehydes and ketones. Next group up. Alcohols, next group up. Then up at the very top are carboxylic acids. So typical question would be, I'd give you 5 things, aldehydes, ketones, alkanes, etc. Which has the highest boiling point, which is the lowest, which is the most soluble in water, which is the least soluble in water, those type questions. So the acids get the highest boiling point. In water. And alkanes are the lowest boiling point and the least soluble in water. And then everything else is in between. Okay, because acids are very polar. They hydrogen bond nicely with water. Okay, so we see that magic number 7 again come up. No, actually it's 8. Count that. So we're looking, this would be C7 plus the COOH. That's where the breakout point would be. And what that means is so that C7 is long enough to have a major influence on the intermolecular force of the molecule. So it now becomes A. So that's the transition into a non-polar molecule. But it started off as a very polar molecule. Okay, when we say carboxylic acids, carboxylic acids are organic acids. They are weak. That means a weak acid, by definition, is one that has less than 100% hydrogen ion dissociation. So let's look at an acid. What is an acid, first of all? Okay, it is it's a compound that dissociates a hydrogen ion. So you have 2 kinds. You have strong acids And you have weak acid, which is less than 100%. Examples, there's acetic acid, palmitic acid, linolenic acid, linoleic acid, and there's a whole bunch of acids that are weak. And there are 7 only strong acids. And you are probably familiar with sulfuric, hydrochloric, nitric. Those are the 3 most common strong acids. There are 4 others, but these are the 3 most common ones. Okay, we're getting back to this here. So in a high pH environment, alkaline conditions or basic conditions, what happens is that hydrogen that's going to dissociate is going to be grabbed by the water. It's going to form a hydronium ion, H3O+. In acidic conditions, if you're starting with the ion, what happens is it protonates. It puts the hydrogen on. So this would be acidic conditions, low pH. So if we start with acetic acid, for example, now in water, plain old water, we are going to disassociate a H plus or H3O plus, just in water by itself, okay? If we throw in strong pHs, high or low, it's going to be exacerbated a lot. So the fact that you call it an acid means that H comes off. So you just say acid. By definition, something's got to come off H plus wise, or H3O plus. Most of the time we just say H plus because we know it's a hydronium, blah, blah, blah. Okay? All right. And it's no longer the acid, it's called the 8 ion. So the other common, that's a common name for a 2-carbon acid. The other one is so this would be OH. So strong base drives out that hydrogen there, leaves you with the salt of the base and water. This is just straight neutralization of an acid. Okay, so whether it's in just plain water or in an alkaline water like sodium hydroxide or potassium hydroxide, you still form the salt. This is the salt. It's also known as a conjugate base. And we're not going to worry about this. This is a 305 designation there. So we're not going to worry about calling it the conjugate base, but that's when you talk about acid-base chemistry, that's what they talk about. Acids and the conjugate base. Okay. So whenever we're naming the salt, we're adding ATE. And frequently, like this would be so the ick goes to the 8. Okay, physical properties. This is the last thing we're going to cover here with acids here. Physical properties of the acids, organic acids. Usually they're solid at room temperature, but not necessarily. Okay, it depends on how long the chain is. These are all acids you're going to have to know. Palmitic, oleic, linoleic, linolenic. There's a series of them. These are all very important from a biological perspective. These all participate in phospholipid membranes. Okay, the sodium salts of long chain fatty acids are used as soap. And we're going to talk about that a lot in a minute here. The combination of an acid plus its salt is how they make buffers. Buffers are used a lot in food because you don't want things super acidic, super alkaline. Alkaline things are bitter, acid things are sour. So you want kind of a balance between those two. And as we go on in this subunit, you'll see how this all comes together. Okay, so I'm going to stop here. I'm not going to talk about esters. All right, so that's a very short intro to organic acids or carboxylic acids. All right, so are there any questions? Oh, and for Monday lab, I'll have your graded test to give out as well. Okay, all right. Well, I guess I'll see you guys. I'll see you Monday lab, folks. 3-ish. For the next wet lab, make sure you have your pre-lab done. I'll be checking for that. It's a much more straightforward lab than the last one. And I'm sorry to say, Monday folks were guinea pigs. Wednesday's lab went extremely well. Nothing was burned. The reason why things were burned is that you had a flat bottom flask instead of a totally round bottom flask. And we used big stirring bars or small stirring bars. Anyway, I worked all that out. So unfortunately. So hopefully when you guys merged your distillate, you got enough to do a density calculation. So, okay. So any last minute questions? Okay. Could someone send me a message to remind me to put the practice tests up for unit 2? Okay, everyone. You're not very talkative today. All right. Well, I'm going to end this now. See you in a little while.